Brian Odom, and he's going to tell us about trapped molecular ions to pumped arbitrary rotational states.
Yeah, the other title for this talk could have just been fun we're having with molecular ions in my group. Pull them down a little bit. Is that okay? All right. So you've gotten a little bit of a preface of this from Dee. We all know that molecules are going to be a lot harder than to control and do things with than atoms because of the more complex state structure. Atoms, it's an old story now how to get quantum control over the hyperfine levels, but molecules, you have vibration, you have hyperfine, but also vibrations, rotations, rotational angular momentum, magnetic moments, all these things. But if you could get these under control, like we can do with atoms, and maybe you could do clock level spectroscopy, like Didi's group is starting to do with molecules, as well as maybe you can do it with atoms. And maybe you can do some quantum information processing. Recent proposal by Eric Hudson and Wes Campbell talked about how you might use a rotational qubit to do some interesting tricks for quantum information. And maybe there are some advantages there that these extra degrees of freedom, you can actually do things that atoms can't do. But all this is, at first, the first thing you have to do is get molecules in the quantum state you want them to be in, and that's challenging. So here's the team at Northwestern working on this problem, and there's our funding. And well, Dee told you this in words. I'll tell you this in a cartoon. Can you use an atom to control the molecular state, molecular internal state? And yes and no. If you laser cool the atom, you can get a nice Coulomb crystal where the molecule is locked in place. But because the molecular length scale is so much shorter than the typical 10 micron spacings, the molecule goes on happily rotating, vibrating, just like it was before. So on one hand, it's frustrating. You can't use synthetic cooling for all the degrees of motion. On the other hand, this is a great plus because you can synthetically cool without disturbing the internal coherences of the molecule if you can learn to talk to them and use them. So this is a picture that one of my graduate students found from the web. Optically pumping the molecule is like filling a leaky bucket. And there are a few different approaches of molecular state control. Dee just told us about this quantum logic sort of cooling. Mikhail Dreyfson has used narrowband optical pumping before. And we're in my group, we use this technique of broadband optical pumping. And so basically this was inspired by the Orsay group, where they used a broadband laser spectrally filtered to control the vibrational states of the neutral cesium dimer. We want to borrow their technique, and instead of controlling vibrations, optically pump down to the rotational level. And the technique goes as follows. You have a femtosecond laser, a mode-locked TISAF, and you disperse it so that on the Fourier plane, different colors land at different places, and you put in a mask, which blocks the part of the light that you don't want, and you regroup the light, and there you get this spectrally filtered pulse. And so the time domain, this is pulse shaping, and the frequency domain, this is spectral filtering. It's the same thing. We like to think of it as spectral filtering because we care about the frequency components. So this is not good for most molecules. That's because most molecules don't have diagonal Frank-Condon factors, so that you have an electronic well of the ground state, which is generally offset, and not only is offset, it generally has a different spring constant than the electronic excited states. And so when you drive an electronic transition for most molecules from D equals 0 to D equals 0, you'll tend to relax into a different vibrational state. And so angular momentum selection rules always allow you to cool rotations if you just take out the delta J plus 1 parts of the spectrum. However, it doesn't do you much good to drive delta J equals -1 if you drive delta D plus 3. So we want to work with diagonal Frank-Condon molecules, where basically you're driving the valence electron from a non-bonding orbital to another non-bonding orbital, and then the chemical bond doesn't care that you messed with the electron. And so these wells have the same spring constants, and they have the same equilibrium distance. And so that more often than not, you'll get delta D equals 0 on the electronic relaxation. And so our favorite molecules so far are ALH plus and SiO plus, and they have they're diagonal to about 97%. So that means you get about 30 photon scatters before you get a vibrational excitation. And so that feature gives you delta D equals 0 in electronic transitions, spontaneous emission events. But there's another important thing also which I haven't touched on yet, which is the rotational heating transitions. The delta J or delta N plus 1 are well separated in these molecules from the delta N minus 1 transitions. And this is a feature of having these equilibrium distances almost the same. The rotational constants of these two states are approximately equal. And so that means that spectral filtering in these molecules, these special molecules, is particularly easy. You just block this part of the spectrum, and you illuminate the sample with this part of the spectrum. And so just a simple cutoff mask suffices. And this is a spectrum we took at SiO Plus in collaboration with Tim Steinley's group at Arizona State. And again, I need to give credit. The diagonal Frank-Condon factor idea has been around for a while, from DeRosa, and then used in the neutral world by these folks. But then Ken Brown's and my group were the ones that realized that this could be useful for rotational cooling of molecular ions. So that's what we use it for. Let me just show you the history. We used it first for ALH plus, and we got from 4% thermal population in the N equals 0 state to 95% in the N equals 0 state, just with this simple spectrum filtering technique. So back to the slide. Let me show you what it looks like on the table. It takes up a bit of table space, about a meter, all said, but not so bad. Once the expensive thing here is a femtosecond laser, but all the optics are off the shelf, and we use 1-inch optics and a 1-inch sort of grating, and it's not so bad. So ALH plus were great for this rotational state control, but there are several things we didn't like about it. One, it has too much hyperfine structure. The aluminum, there's nowhere anywhere near a spin equals 0 aluminum isotope. And also the rotational transition is not that accessible. As Dee said, it's in the terahertz for hydrides. So my postdoc at the time, Jason Wynn, realized that SiO plus might be a better way to go. This species has a few attractive features. There's one dominant isotoper, 0 nuclear spin, microwave accessible rotational interval of 40 gigahertz, relatively large body frame electric dipole moment of 4 to pi. So if you want coupling between different molecules in your trap, this is perhaps doable with this large dipole moment. The state lifetimes are many seconds, limited by a black body to an intermediate state, which I'll tell you about in a moment, and some other features making fluorescence readout a possibility with this species. So it comes along with challenges, though. First of all, the spectrum, the P branch from the R branch, or the delta J -1 from the delta J plus 1 branches for oxides is closer together than for hydrides. And so our spectral cutoff has to be better. We have to do on the order of 80 gigahertz instead of 400 gigahertz for the hydride. And there are many more populated states at 300 Kelvin. So here we started with 4% in the target state. And here is a pie chart for SiO plus, and you can't even see the target state at n equals 0 showing up in the pie chart. It's so small. So it'll be more challenging to pump this molecule into a given quantum state for a number of reasons. So we struggled with this species for a while, years in my lab actually, until the right teams came together. And these folks, Pat and Ivan and Sruti, have been fantastic. I especially want to give credit to Ivan, who's a chemistry postdoc from a chemistry background, and he's on the chemistry job market right now. He wants to use ion traps for chemistry purposes, and he told us a lot of tricks that chemists knew, but we didn't. And so then finally we started making progress on this species. One thing that he showed us how to do is load the right molecule. We had been working with, similar to how Didi said, we had been bleeding in oxygen to try to get silicon to react with O2 to give us SiO+. We found out that actually we were getting mostly SiOH by accident, and so that wasn't any good. So Ivan showed us how to ablate a neutral sample of SiO and then photoionize it with an OPO with a process which gives us the species that we actually want, SiO+. And here you see it synthetically cooled SiO+ in the core of a barium Coulomb crystal. And barium are our workhorse atomic ions that we use to synthetically cool. So here's what the structure of the species is like. The ground state is called X, and the electronically excited state, which is nearly diagonal, is called B. And that we drive at 365 nanometers. It's a double mode locked laser, spectrally filtered, of course. And then, so what else is here? There's this A state that you might worry about. Not the thing you want, because what if the B relaxes to the A? But it turns out that's actually kind of rare. That involves two electrons changing their configuration to go from B to A, and so it doesn't happen very often. And if it does, well, to get from A to X is only a one electron configuration change. And so this actually, A to X happens at millisecond time scale, and B to A happens, I forget the time scale, but not very frequently. So if you ever get there, you're dumped back into the well you want to be in pretty quickly. And then we need a tool to tell what rotational state we were in. And for that we use a destructive technique where we do a photodissociation, which only talks to one rotational level at a time. Now usually to get state selective photodissociation, because you're going from bound to an unbound interval, usually you need to use a two-photon process where you go bound to bound and then bound to unbound, because unbound states don't live very long, and so you don't get very good frequency resolution. However, this species has a special feature that there's this quasi-bound state here, and the quasi-bound state happens to live long enough for us to get rotational resolution, even though we're dissociating with a single 230 nanometer photon. So that two-photon dissociation would be fine to do too, but it's a little bit easier to do one-photon dissociation for a rotational readout. So let me get into the weeds just for a little bit. The trick now is going to be telling what our species composition is. How much Si plus do we have in the trap, and how much SiO plus do we have in the trap? Because remember, if we're in the target end state, then we transform this species, we break it apart, and we end up with this species. And so we need to count the relative fractions of SiO plus and Si plus. The simplest and actually most accurate way to do this is to dump the trap and use time of flight to tell the difference. And that's easy to tell the difference between this mass and this mass. However, it's slow. You don't want to dump the trap every time you want to make a measurement. I'm going to get another cough drop out here. I'm recovering from a rather nasty flu, so apologize. Cover your ears. All right. So it's good but slow. The other technique we use, and Mikhail Dreyfus's group has done this along with Stefan Schiller's group, has shown that this works too. If you want to know what the dark species is, well, use your bright species, your barium fluorescence in this case, and just tickle the resonance, the secular resonance of the dark species. And if you have an all SiO plus sample, then you get a dip in the barium fluorescence at that frequency, at that resonant frequency. And if you have the Si plus sample, then you get a dip at a different frequency. And if you have a mixed sample, then you get a little bit of a dip at each frequencies. And this is nice because you don't have to dump and trap. It does have some drawbacks though, that these species are not completely decoupled from each other. So as the relative numbers change, the resonant frequencies of these dips shifts a little bit, and that can cause you problems for your for accurate determination of exactly what the dark species composition is. But it is useful for dynamics. And so, for instance, if we want to know how long does our SiO plus remain in the trap, we can intentionally elevate the background gas to 5 by 10 minus 10 torr, and watch for the reaction, the SiOH plus. And you can see this tickling resonance shifts over, corresponding to 1 mass unit of difference on the 10-minute time scale or so, or several-minute time scale. And this answers the question also, if you get SiO plus in the trap, how long do you have to work for it? And even at a bad vacuum, you have several minutes. So then I wouldn't have time to go through this in great detail, but this is one of Ivan's main contributions to the group. He realized an even better way to tell at least relative populations. And that's, you instead of doing things in bursts, you continuously do things. So you continuously optically pump into your distribution that you want. You continuously try to photodissociate from that target state. So you're trying to break apart molecules as fast as you can. But you set up the timescales so that your photodissociation is much slower than your pumping. So every time the photodissociation event happens, you're essentially looking at the equilibrium or pumped distribution, and you're making a fresh measurement of that distribution for every photodissociation event. And then you just now tickle at SiO plus resonant frequency, and actually you can account for the nonlinearity I told you about before by covering a small span of frequency. So if it shifts, you don't care, you hit everything. And then okay, so the photodissociation has a certain probability per unit time of happening, but then you pay the penalty of how much of your population is in that target state. And so you get, what you end up with is a different exponential destruction curves. You destroy your sample eventually, either way, but you destroy it faster if you have more of your population in your target state. And so, at least for a relative measurement, you can just look at how fast the sample is destroyed from one pumping scheme to another, or one target state to, versus another. And this exponential of the destruction tells you how much relative population you had in the target state. And so by looking at these exponential curves, we can get fractions, relative fractions of how well we were doing optically pumping.
You like some water, Brian?
No, I need to be less congested, but thanks. Water won't help. So let's see how it works. First, we'll just apply the simplest mask of trying to pump all the population into an n equals 0 state. So we'll block the P branch light that drives at delta n plus 1 transitions, and we'll let through the rotationally cooling light. And so then, of course, our photodissociation spectrum will tell us what states we were in. And so after the trap loading, you'll notice the photodissociation spectrum is a gigantic mess. Over a huge range of frequencies, you see photodissociation signals. And it would be ugly enough for a thermal distribution. That's plotted in blue here. But we have nothing like a thermal distribution right after trap loading. And it's not surprising because we're loading from photoionization, so it's no one says that you'll produce a nice thermal distribution after that, and we don't. But then we apply this simple mask where we try to get all the population in the n=0 state, and the spectrum cleans up very nicely. If you look more closely at the spectrum, if we had population entirely in n=0, then we would only have a photodissociation line here and there for driving the Q and R branch of the photodissociation transition. Instead, we don't have 100% population in the n=0 state because you can see a little bit of a signal from there and a little bit from there and there, telling us that we have about 90% in the ground state and about 10% in the n=1, and a little bit of residual in n=2 and higher. But 90% on basically the first attempt, we were not dissatisfied with that. And so looking at the pie chart again, this is the 300 Kelvin distribution with the blue target state not even showing up on the graph. And after applying this simple mask, we get 90% of the target state, which corresponds to going from 300 Kelvin or hotter, actually not a thermal distribution, to a little bit less than a Kelvin. And that happens on, here's our measured time scale. On the tens of milliseconds time scale, we cool one parity. But then, one photon up and one photon down doesn't change the parity. So you need some mechanism to get an odd number of photons in the process to get parity cooling. And that is set by a spontaneous emission time scale where B relaxes to the A state and A relaxes back to X. And then on the seconds time scale, we can get parity cooling as well. And we get approximately 100% or 90% of the population in the target state. And then how long does it stay there? Well, if it were black body, it would follow this blue curve. It appears that we have slightly faster than black body. Our state lifetime is around 20 or 30 seconds. And most likely that's due to collisions with background gas, redistributing the rotational states. Okay, then I told Pat that he should just graduate because those were great results, but he wanted to try to cool at the higher end. And so he made this very sophisticated mask with black tape and a wire hanging down. And the idea here is that, well, and this is his newest version of the mask, which is only slightly more sophisticated, where he has different gauges of wire in his tool. He walks around with these on his belt. And you have two different razor blades to block the parts of the spectrum. The coarse parts of the spectrum you don't want in there. And then you block a narrow band of the spectrum with this wire of varying thickness. And what that allows you to do is create a filtered spectrum like this, where you now allow in part of the delta n+1 light, but only in a certain band, up to n=10, say. And then you don't cool all the way down to n=0, you only cool down to n=10. And so you can, by making masks like this, you can target any rotational state you want. And for instance, this is how well his cooling into the n=10 state worked. It's more challenging than cooling into n=0, for one thing, because the spectra are more congested away from n=0. But still, he gets a pretty respectable for a first try distribution around n=10. And then he can be more ambitious. He can try to cool up to n=50. And you see the photodissociation spectrum is changing very dramatically. this is okay. For all these cooling targets, the temperature is very low. It's 10 Kelvin or lower, even up to n equals 50. And that's because you have a narrow distribution of quantum states. But the Boltzmann peak, if you use that as a temperature, it's actually a very energetic sample. So it's sort of like a supersonic beam. You have a cold sample, but it's moving with a high forward velocity. We have a very energetic rotation, but a very low temperature, because we have a very narrow distribution of quantum states. So then, Pat still didn't want to graduate. He wanted to push it even farther. If you use these simple masks that I told you about, you have a problem, because the heating branch turns over, and you start getting, you apply light at a given frequency, and you're driving transitions that you don't necessarily want to drive. And it's worse when you consider the excited vibrational state, which I don't have time to tell you about. But if you're more sophisticated and you have a dynamic mask, and which you change in time, then you can kind of drag the population with you along even past this curve. And so right now, we actually have a very simple mask. We use a motor to cool from up to n equals 50, and then we flip to another configuration, and then we only shine in our branch light, and we drive the population up from there to whatever cutoff we apply, and eventually we'll reach equilibrium depending on where we apply the cutoff, because spontaneous emission will compete. Spontaneous emission at these high ends, these are very far apart levels. It's milliseconds up here, and so at the edge of the spectral cutoff of our mask, spontaneous emission is taking you down as far as our P branch light is as quickly as our P branch light is taking you up, and so we can equilibrate basically anywhere we choose. And in the last few months, we've done this, done a few fun things with this, which let me take you through now, although it's still pretty preliminary. First of all, we can do some exotic chemistry at these high rotational states. So if we just have a thermal distribution, and you ask how much time does it take SiO plus to turn into SiOH plus? Well, at a certain vacuum, it's around 700 seconds, and that's about 20% of the Langevin rate, which would be the maximal possible rate for an ion neutral reaction. So this is a reasonable number, 20% of Langevin. But then when we pump up to these highly excited rotational states, we measure a noticeably different reaction rate curve. And so somehow the molecular rotation is affecting how fast this chemical reaction goes. And we don't fully understand what's going on there, but we have some preliminary theory from a collaborator, Wagao, who here's his theory for intermediate states in the SiOH plus, right, SiO plus H2 reaction. And the thing to point out here is that if the hydrogen approaches the oxygen end of the molecule, then the reaction seems much more favorable than if it approaches the silicon end. And so why would that be important? Well, for n equals 0, one way you can do it is compare linear velocities. So hydrogen at room temperature goes at around 1,800 meters per second. And for the n equals 0 state of SiO plus, the center mass, if you turn that into a linear motion, is moving at 40 meters per second. So the hydrogen is flying by, and the molecule is essentially stationary for every time a hydrogen molecule flies by it. But up at that's supposed to be n equals 170 typo. But up at these high ends, the molecule is actually moving much faster. So you can speculate that every time a hydrogen flies by, it sees the favorable end of the molecule that it wants to react with, and then the reaction goes very quickly. And so this could explain a factor of 2 in reaction rates. And this is sort of exotic state-dependent chemistry. we have to finalize this story, but it seems plausible at the moment. Another thing that we've done with this high state control is we've done some spectroscopy. Ivan is a physical chemist by background, and so he said, hey, we can do this for some spectroscopy that's kind of hard to get at with conventional techniques. So if you had a thermal spectrum and you wanted to investigate this particular transition, the electronic C state to X state, the vibrational 1 to 0 transition, here's what the distribution would look like of those transitions. And especially toward a higher N, it's a mess because of various kinds of overlaps. But when we prepare our population in a narrow distribution of rotational states, here's what theory says it should look like, those blue sticks. And we get spectra which are basically agree. There are a few wrinkles in the story, but they're certainly less congested than the non-narrow distribution would be. And from this spectra that we measure, we can assign lines, and we can, for instance, extract a centrifugal distortion constant very easily. For n equals 0, this would be relatively hard to extract. It's a part of 10 to the 6. But for n equals 60, it's because of the end of the fourth dependence, it's actually an easily measurable quantity. And so this isn't anywhere near as good as the centrifugal constant, which Dee Dee showed you earlier, but it's pretty easy to do in our case with on a large sample with this rotational state control. And then there are also interesting features. You notice these progressions of lines tend to have some sort of Gaussian envelope to them, except here where this guy is lower than his neighbors. And this we've assigned to an avoided crossing at another molecular energy level. So we can do you can use this for a novel approach to spectroscopy to answer questions that might be hard to get at with conventional techniques. And then the final application of the state control is to wreak havoc on the system. So we notice that as we spin up to these really high rotational numbers, the molecules start falling apart. We have a dissociation rate of 0 until we hit some threshold of around 196, and then we see the molecules break apart at around 10th of a second. So we don't understand what's going on here, but there are some ideas we have, and let me take you through one of them. So how much time do I have? 5 minutes, okay. So that'll be fun. So to get these high rotational states, remember we're pumping to an equilibrium between spontaneous emission and our pumping laser, both driving at equal rates. And so our population is often in this excited B state. Okay, so here's what the B state curve looks like for n equals 0. Look at the blue curve. And because of avoided crossings with one level which we drew here in orange, it has a funny shape. But basically, this is a very deep potential well. And so you're nowhere near dissociation. But when you add the centrifugal term up at n equals around 200, this is a much smaller barrier to tunnel out of. So if it were tunneling to dissociation, that would be interesting. Let me just say a few words about that. I taught this last week in my graduate quantum mechanics class. This looks kind of like a finite square well, right? Where there's a certain part of the wave function, even though it's quasi-bound, there's a certain part of the wave function out here, and that results in tunneling on some time scale. But if you think in 2 dimensions, it's a little more interesting than that. For a given angular momentum quantum number, you could have 2 configurations. You can have a molecule bound and rotating with that angular momentum, or you can have a scattering event where the call it the oxygen comes in and tries to attach to the silicon, but it misses. It kind of slingshots around, and both of those configurations can have a well-defined angular momentum. And so, but in between, there's a forbidden region. There's a forbidden distance between the silicon and the oxygen where there's no allowed state, and that corresponds to the barrier. And so this molecule, the oxygen, might figure out, hey, I can get away from the silicon. If I change my spin configuration and jump over the forbidden distance, I can run away from this bond that I don't really want to be in. And so it might be tunneling through the centrifugal barrier. It might not be, but if it were, that would be interesting. There are some questions about that hypothesis, like why is this appear linear when you would expect an exponential for a tunneling process? But anyway, we're still working out that story. What's clear, though, is that we can spin the molecules up fast enough that they fall apart. So something interesting is going on there. So what else might we want to do in the future? Well, you could imagine using state-controlled molecular ions as a black-body thermometer. The black-body response of the molecular spectrum really spans a bunch of the black-body spectrum. So vibrations cover the black-body spectrum up there, and rotations down there. And so if you could state prepare your molecule in any given quantum state, then you could probe for an atomic clock, for instance, what really is the blackbody distribution that the atomic clock is seeing. Imagine co-trapping molecular ions, state prepared, and using that as a probe of the local blackbody field. Another thing that you could imagine doing is preparing molecules for quantum information processing, not in the n=0 state, but in n=10 or 40 state. And that could have some advantages because decoherence mechanisms are slower at higher ends, at least up to a certain point until you start fighting with spontaneous emission. So again, preparing arbitrary quantum states might be interesting for quantum information processing of molecules. So in conclusion, I've described to you the technique of broadband rotational cooling. This is using special molecules, the sort of alkalis of the molecular world. Those are diagonal Frank quantum factors. It's a limited set, but with that set you can do a lot. And this uses a single laser for optical pumping, and you can cool into the ground rotational state, or actually we've shown now into basically arbitrary rotational states. And in the future we want to add a vibrational control knob to prepare vibrations and use a more sophisticated version of these dynamic masks like a MEMS array. And we also want to do the NIST-style single molecule spectroscopy work with an optical pumping tool in hand, and we're looking for a postdoc for that experiment. So if you have one available, let me know. And with that, I'll conclude. Thanks.
Question?
Yeah, maybe yeah. I'm not sure that I understood your story about this tunneling effect. I mean, these two configurations that you are talking about. So, could you tell it again?
Yeah. So the angular momentum is conserved, right? And so if the oxygen is going to escape from the silicon, it has to do it with the same angular momentum of the entire system. Okay. And so there are two different configurations with, at least for high end, for n=190 angular momentum, for that angular momentum you can either be in a balanced state, or you can be in a state where the oxygen is approaching the silicon but misses and flies away. And
you miss on the other side of the barrier, right?
Yeah, in 2 dimensions, it looks like a slingshot. It goes around the molecule and comes back out. And so both have the same angular momentum, and so you can get from one to the other if their tunneling barrier is is in the right shape.
Okay, yeah.
That's basically it.
I was intrigued by your novel molecular spectroscopy at high end, and I was wondering if you're making enough molecules to do a precision spectroscopy with them. You may be limited if you only have a few molecules, right?
Yeah, so it's a great question. We haven't looked at how far we can push that. Right now, we typically work with 100 molecular ions at a given time, but that could be 1,000. We're limited by the size of our cooling laser beam.
Right.
We want to saturate the transition or approach saturation, and we can't make that beam too large. Molecular ions are far apart. But we could certainly push the numbers higher and perhaps do some interesting precision spectroscopy.
One more question.
Yeah, I was wondering, for your tunneling or not, is there a chance that it's simply collisions, and since you're at higher rotational energy, you just have more energy to get out of the well?
Yes, collisions or black body vibrational excitation are two different mechanisms that we're thinking of. Neither, when we've thought a little bit about those hypotheses, and neither makes good sense to us right now. But yeah, it might not be tunneled.
Okay, let's thank all our speakers again. And